let's talk about an invisible architect, a master builder that works on a scale so small it's hard to even imagine, the atomic scale. This is the force that designs the very structure of the materials that build our modern world. And today, we're going to learn how to read its blueprints.
I want you to think about your smartphone for a second. You might even be watching this on it right now. On the outside, yeah, it's just a sleek piece of glass and metal. But what's really going on inside? What makes it all work?
Well, the magic is all in the stuff you can't see. Deep inside that phone are these incredibly complex, thin films. We're talking layers of materials that have been engineered literally atom by atom, some of them thinner than a single wavelength of light. These invisible layers, they are the real building blocks of all modern electronics.
Okay, but that creates a huge problem, right? If you're an engineer trying to design the next big thing, how in the world do you check your work? How can you be absolutely sure those atomic layers are lined up exactly the way you designed them when they are completely, totally invisible?
The answer? You have to learn to see with a different kind of light. And this is where we meet the hero of our story, X-ray diffraction, or as we call it, XRD. This is the amazing tool that lets us finally read the atomic blueprints of matter itself.
So, how does this thing work? You know, imagine you're throwing a tennis ball against a brick wall. Just by looking at the angle it bounces off, you could probably figure out how the bricks are spaced out. Well, XRD works on that exact same principle, just on a ridiculously smaller scale. It uses high-energy hex rays as the tennis ball, and the material's own atoms as the bricks.
And the whole thing is governed by this one beautiful little piece of physics, the Bragg equation. Think of it as the secret decoder ring. It connects the wavelength of the X-ray, which we know, and the angle it bounces off the atoms, which we can measure, to the one thing we really want to find out, the exact distance between those atomic layers. This equation is what turns a simple bounce into a precise blueprint.
Now, of course, just like with any super precise tool, you can't just wing it. You need the right setup. For those ultra-thin films we find in electronics, scientists almost always use what's called parallel beam optics. It's just a smarter way of focusing the X-rays that helps avoid a bunch of common errors. You get cleaner, more accurate data. Simple as that.
So now that we've got the basic idea down, let's see how this actually works in the real world. You see, XRD isn't just one measurement. It's more like a whole toolkit. And each tool, each scan, is designed to answer a totally different question about a material structure. We're going to walk through the 5 essential scans you need for analyzing thin films.
Okay, first up in our toolkit is the symmetric scan. This is your ground zero, the fundamental measurement you pretty much always do first. It's like asking the most basic question you can. What is this stuff anyway?
And this scan answers 2 really big questions. First, what's the crystalline phase? Is it quartz or is it silicon? And second, what's its out-of-plane orientation? That's just a fancy way of asking, how are those atomic layers stacked one on top of the other?
All right, next up we have something called grazing incidence XRD. The name kind of gives it away. The X-rays come in at this really shallow grazing angle. And that's no accident. It's a super clever trick to make sure the X-rays only interact with that super thin top layer, while pretty much ignoring the thick material underneath it.
And what's so cool about this is what it accomplishes. It essentially filters out all the noise. The signal from that thick material underneath, the substrate, is usually overwhelming. This technique turns that volume way down, so the tiny, faint signal from the thin film can finally be heard loud and clear.
Tool number 3 is the rocking curve. Okay, so if the first scan asks, what is it? This one asks a different question. How well is it made? It's basically a quality control check for how perfect that crystal structure really is.
So this can measure things like epitaxial quality. Now all that means is, how perfectly does the atomic pattern of the thin film line up with the pattern of the material it's built on? The sharper the peak you see on the graph, the more perfect, the more ordered, the higher quality your material is. And trust me, that's absolutely critical for making sure a processor actually works. But what if you need the whole picture? I mean, the full 3-dimensional story? Well, that's when you bring out the big gun, the pole figure. This isn't just one measurement from one angle. Oh no, this is a comprehensive scan that builds a complete 3D map of how the crystal is oriented in space.
What you get is this incredible map that shows the complete texture of the film. It tells you exactly how all the different little crystal grains are oriented in 3-dimensional space. It is by far the most detailed view you can possibly get of the material's atomic architecture.
And last but not least, we have the azimuth scan. Now I want you to think of this one as a clever shortcut. A full pole figure, that can take a lot of time. So if all you need is a quick answer about the horizontal alignment, what we call the in-plane orientation, this scan gets you that data fast. It's the perfect spot check when you don't need the whole shebang.
Okay, so we've run our scans, we have our data, and it usually looks like a graph with a bunch of spiky peaks. So what now? What does any of it actually mean? How do we translate these squiggly lines into a real blueprint for the material?
It all comes down to learning the language of the peaks. Where a peak shows up on the graph, its position tells you about the material's chemical makeup and whether it's under stress, which could cause a device to fail. How tall the peak is, its intensity, reveals how well-ordered the crystal is. And even how wide the peak is contains a ton of information, giving you clues about the size of individual crystal grains, which can affect a material's strength.
And this is where things get really clever. It turns out two different things can make a peak wider: having really tiny crystal grains and having a lot of internal strain. The Williamson-Hall plot is this ingenious analytical trick that lets scientists untangle those two effects so they can measure each one all by itself. So, those 5 scans and analysis methods, they're really the heart and soul of thin-film XRD. But trust me, we've only just scratched the surface. The rabbit hole goes way deeper.
There are all these next-level techniques, like reciprocal space mapping, for sorting out incredibly complex structures with many layers. There's X-ray reflectivity, which can measure a film's thickness with atomic precision. And there's even in situ XRD, which is amazing. It's like getting a live stream of the atoms, watching them rearrange themselves in real time as you heat a material up or apply voltage to it.
So, at the end of the day, why does any of this matter? It matters because being able to see and verify the invisible atomic structure of materials is literally how we build the future. All the cool stuff we want, more efficient solar cells, faster computer chips, you name it, all of that progress starts right here, with being able to control matter at this fundamental level.
So, I guess I'll just leave you with this thought. We now have the power to read the atomic blueprint of pretty much any material. The only real question left is, what do we want to build next?